Hi everybody, this video today is going to cover lesson 5.7, which is the fundamental theorem of algebra. If your numbering is a little bit different, you might just want to adjust that to 5.7. The fundamental theorem of algebra sounds super important, and it is, but we have actually mentioned it before when we did this activity the other day. When solving an nth degree polynomial equation, there will be exactly how many roots. And we talked about this, that there's going to be n number of roots if it's an nth degree polynomial. So for instance, x to the fourth will have 4 solutions. And you know what? Maybe up here at the top we also need to talk about, we talked about some synonyms ever since the beginning of the year. We've talked about these synonyms, that the words roots and the words x-intercepts and the words solutions, and there's another word that I always forget out of my list, but these words all mean the same thing. So when I talk about solutions, roots, they're all the same thing. All right, let's also talk about some of the vocabulary that's here. It says this includes rational and irrational solutions, complex solutions, and repeated solutions. What does that mean? Well, rational numbers are basically numbers and fractions, like normal, good old-fashioned numbers. Irrationals are going to be square roots, and non-repeating decimals is part of the definition, but what we are really focusing on here in this unit is square roots. And then complex, those are like imaginaries. And then repeated solutions is if you have something like x to the second, that counts as 2. Anytime that, whatever power that is going to count as that many more solutions. All right, let's look at the complex conjugate root theorem. We're going to continue to tie all of this together. It's just a lot of stuff kind of going on at the same time. So if a plus bi is a root with a real number coefficients, then its conjugate, which is a minus bi, is also a root. So we have talked about some of the roots and how we have rational roots and irrational roots, and now today we're going to talk about irrational roots and some complex roots. So we need to talk about the a plus bi. Well, if a plus bi is a solution, then a minus bi is also a solution. What do I mean by that? Well, that means if 2i is a root, then so is negative 2i. Or 8 minus I, if that's a root, so is 8 plus I. And guess what? If 3 plus 4i is a root, guess what else? 3 minus 4i. So we keep the same numbers, we just change that sign to a minus sign. And so the roots always come in pairs. That's important for us to remember. Come in pairs. All right. So we're going to use that information here in this one because this is write a polynomial function in standard form with zeros of these. So if we knew what the zeros were, then we can make factors out of them. For instance, x equals 2, that really means that the factor is x minus 2. And if x equals 5i, then the factor is x minus 5i. And then we just learned this rule up here. If 5i is a factor, then so is negative 5i. So that means we also have a factor of x plus 5i. Okay, so here are our factors, and it says a polynomial function. So this is our function. This is our f of x. This is our function. This is in factored form, but we need it in standard form. I have a little hint for you to multiply the conjugates together first, and we actually worked on this a little bit last week as well. So I'm going to multiply these two together because that's going to make it a little bit easier for me, isn't it? And I think hopefully we remember that's going to give me x squared. And then as I go through here, that's a plus 5ix minus 5ix. Those cancel each other out. They drop off. And so now we have minus 25i squared. Now, do you remember back from our imaginary unit what I squared is? Well, I squared is negative 1. So this is actually, the function we're looking for is x minus 2. And then this is x squared plus 25. Okay, now, but we're not done yet because it says in standard form. We have it in factored form, in a bunch of different factored forms, but we need it in standard form. So we need to go ahead and multiply this out. You take a second and multiply that out. All right, depending on what order you had it in, I had to take kind of a step in the middle here, but then when I put it in standard form, my x to the third comes first, minus 2x squared comes next, plus 25x minus 50. So the question was, write a polynomial function in standard form with zeros of these. We had to add this one to it, and when we multiply it out, this is what we get. Let's take a look at another example. So in that last problem, we started with factored form and we got down to standard form. This problem is starting us in standard form and it wants us to find the roots. Remember, roots means solutions, so we need to solve for x. How do we solve for x? Well, the way we solve for x is we factor it. This can be factored by using the u method. Okay, so our u is x squared, our u squared is x to the fourth. And now we can factor this with the u method. We've been working on this, so will you pause it here, take a minute to factor it. Okay, I'm not sure how far you got. You might have stopped here, x squared plus 9 and x squared minus 4. But remember, x squared minus 4 can be factored again. So that factors down to x plus 2 and x minus 2. So here are my three factors. This is now my factored form, but I'm supposed to find the solutions, the roots. How do I do that? Well, I set each of these factors equal to 0 in order to find my answers. And so the 2 and the negative 2, those are easy, right? We know how to do that. This one is also pretty easy, but we just have to remember a couple of things. We get x squared equals negative 9. I need to take the square root of both sides, so that gives me x equals plus and minus 3i. Do you remember that? The which square root of a negative number is I. So the question is, find all the solutions. How many solutions should there be? Well, there should be 4 because this is a fourth power. So our 4 solutions, here's 1, here's 2, here's 3, and 4, because this is a positive and a negative, so it's positive 3i and negative 3i. There is our 4 solutions. Let's turn the page. All right, this next one is a little bit different because, well, for one, they give us a hint. Wonder why they do that. Well, we need to set this equal to 0. That's a typo. We should have that equal to 0. But they give us a hint. It has 4 terms in it. How are we supposed to factor 4 terms? Or excuse me, 5. 1, 2, 3, 4, 5. We don't know how to do that. We don't know how to factor 5 terms. And so we're going to have to do something with this 4i. What are we going to do with it? Well, we could do division with it, right? But I don't know how to do division with i's, and I don't think you do either. So what else could we do? Well, if 4i is a root, then negative 4i also is a root. Let's come over here to the margin. Wonder what happens when we multiply x plus 4i times x minus 4i. So we multiply this out. We get x squared minus 4xi plus 4xi. Those drop off. And then we get minus 16i squared, which is really x squared plus 16. Okay, we're supposed to find the roots. The roots are solutions. The way we find solutions is we factor. Here is one of the factors, all right? What do we do with that? Well, we can divide it, because when we divide it, then it makes that problem a little bit simpler, right? So, except when I divide, I have to put that 0x in the middle, remember? So I'm going to put that 0x in there, and okay, so I've got my polynomial set up for my long division. X squared times what will give me x to the fourth? Well, that would be x squared. I now have to distribute that. So take a second to finish this out here. All right, so I distribute it. I need to subtract it. And I need to bring down my 16x, minus 16x. How many times does x squared go into negative x to the third? It goes in negative x times. I'm going to distribute that. Okay, I distributed it, I subtracted, I brought down my negative 96, and I'm going to say that I need a minus 6 here, right? X squared and a minus 6x squared. I need a negative 6 up here. I'm going to distribute this again. And so when I do that and I get this, I get no remainder because the more we're subtracting, so there's no remainder. So this is what I have. So what I have so far is x squared plus 16 times x squared minus x minus 6. I'm supposed to find the roots. Roots is solutions. That means I need x equals. Well, I already know x equals 4i and negative 4i, but what else? Well, I have this trinomial, and this trinomial will give me some more solutions. How does it do that? Well, I factor it, of course. So I need to factor this. It does not have a leading coefficient, so I can just do basic negative 6. What multiplies by negative 6? It adds up to be negative x. So that is x minus 3 and x plus 2. That means my solutions are positive 3 and negative 2. All right, those are my two solutions, plus I have these two solutions. There are supposed to be 4 altogether. I have all 4 of them. X equals 3, x equals negative 2, x equals 4i, and x equals negative 4i. Those are my 4 solutions. All right, let's talk about a little bit of graphing. What does a cubic look like? Well, one thing that a cubic could look like is it could look like this. And again, we've talked about this a little bit the other day, but that means there are 1, 2, 3 solutions. What do I mean by real solutions? What I mean is they're real solutions. They're on the x-axis and we can see them. There are no non-real solutions in this case. But we could manipulate this, couldn't we, to find another way to draw it? For instance, I'm going to say we can find one that just has one real solution instead. How would you draw that? Well, you could basically take the same shape. You might make it less curvy or more curvy or whatever, but in this case, there is only one real solution. But the fundamental theorem of algebra says if it's a cubic, that means x to the third, there must be 3 altogether, so there must be 2 non-real solutions. Where are they? They're up here. We don't know what they are. You will find out how to do that in a later class, but for today, we're just saying there's 2 non-real solutions. Okay, is it possible of 2 real and 1 non-real? So think about if you drew this, could you draw it that way? Think about that for a minute. And the best way I can think about it is, well, maybe, let's say it bounced off. We've talked about those bounces before. How about that? Would that give me 2 real and 1 non-real? No, because actually this spot right here counts as 2. Because we've talked about that, how if it's an x squared, it bounces off, so that means there are 2 of them there. So this answer is no, it is not possible. So that was for cubics. Let's talk about, well, what if it's a 4th degree, 5th degree, 6th degree, whatever. Okay, well, let's talk about 5th degree. If you recall, 5th degree means that one side goes up, one side goes down, kind of like this. I'm trying to count here. Did I make too many, or is that okay? I think it's okay. Let's see. So we have 1, 2, 3, 4, 5. That is a 5th degree. So we could have 5 reals and no non-reals. How else could we draw this? Well, maybe we move this bump up here a little bit. So now we have 1, 2, 3 reals, and we must have 2 non-reals up here because they always have to add up to 5. You have to have 5, so that's going to have to be 5. We can move both bumps up there like this, and we just have 1 real and 4 non-real. Again, they have to add up to 5. 5 plus 0 is 5, 3 plus 2 is 5, 1 plus 4 is 5. The sum of each combination has to be 5. Is there any way to get 0 reals? Well, there's not, because you have these like tails on the end that go on for infinity, right? So there's no way to move the axis where it won't hit it. Another thing is we just learned we had 2 different theorems. One of them was the complex conjugate root theorem here, and one of them was a couple pages ago, which was the irrational root theorem that says if one is a root, then the other one is also a root. If plus bi, then a minus bi, and they always come in pairs. We had the same thing with radicals. So this column, this non-real column, always comes in pairs. They always have to be even numbers, 0, 2, 4. The real numbers, you could have any combination, 1, 2, 3, 4, 5, whatever, but these have to be even because they always come in pairs. So for 6th degree, for instance, we could have 6 non-reals, 4 non-reals, 2 non-reals, 0 non-reals. 6th degree is going to look a little bit different. It's kind of more of a W, just with a bunch of bumps in it. Okay, so here's our 6th degree. We could have 1, 2, 3, 4, 5, 6 that are all real and no non-reals. And then again, we can kind of move those bumps however we need to. We can move the whole thing and have 0 reals and 6 non-reals, or we can move the bumps in other ways in the middle. And so 2 and 4, and I'm getting these numbers because again, they have to add up to 6. All right, we covered a lot of ground here, so we will talk about a summary and try to answer questions. If you have questions on this video, make sure you're writing your questions down on the margin so you can ask those in class tomorrow.